AFM discussions here. Well, we are on tapping mode. How do we control the parameters to achieve high resolution in AC mode? Here I use the word AC mode. That's because it's very complicated to describe. Some people call it tapping mode or non-contact mode. Some people call it intermittent contact mode or wave mode. All these terminologies are used to describe the tip and sample engaged in an alternating format in contrast to contact mode. So, what is tapping mode or non-contact mode? How does the tip engage with the sample? And how do we use this knowledge to increase the resolution? So let's look at when the tip and sample engage each other at a certain distance. For example, here, 20 nanometers, tip and sample started to attract to each other because of the van der Waals force. As the tip getting closer to the sample, this attractive force is getting stronger and steeper until the tip started to engage, started to invade the space of the sample. At that moment, the attractive force quickly turned into a very sharp repulsive force. That's basic force interaction between tip and sample. Let's take a look at the cantilever as an oscillator. The vibration of this cantilever, you can view it as an harmonic oscillator, and the frequency, the resonant frequency, is defined by its spring constant and its mass. Now, in real world, the resonant frequency actually is not that simple. It's not only defined by the spring constant, but also there are dampings around it. And this increase of damping is actually will cause the resonant frequency to shift to lower frequency. And when the tip and sample getting close to each other, this damping will increase. Not only this damping increase, tip also will experience a attractive or repulsive spring constant from the sample itself. Let's take a look at how these attractive repulsive force gradients between tip and sample impact the resonant frequency. As you can see, when the tip is experiencing attractive force, in this case a negative force gradient, the tip is pulled into the sample, and as if there is a spring, pull the tip into the sample, which causes the spring constant to decrease. And as with tip and sample engaged in the positive region or repulsive region, the spring constant will increase, which will directly cause the resonant frequency to shift to the left and then a shift to the right, because the force start from a negative force gradients into positive force gradient. And here, look at this resonant frequency. If we put a driving frequency at this F0, and as the resonant frequency shifts to the left, we look at the phase actually also shifts left, and as the tip and sample getting the repulsive force, the phase is actually going to shift to the right. In the real world, not only the resonant frequency will shift, the amplitude also is going to shift. It first will shift to the left. As you can see, the peak slightly move to the left, and then they'll move to the right. This is an experiment, very interesting experiment, and you can actually measure this force by tapping on a cantilever with another cantilever. So you can use the one cantilever to do tapping or AC mode, AC interaction, by manipulating its drive and set point, and using another cantilever to use its deflection signal to measure the repulsive attractive force. And then you can see here that it resembles some kind of force curve here, and now you can tell that even in AC or tapping mode, tip and sample still have a force, and it will have its attractive region and repulsive region, just like a static force curve. So let's take a look at here we call it phase curve, and how do we understand a phase curve? Because in AC or tapping mode, we use the phase curve to study the interaction between tip and sample. As you can see here, the red is phase curve. It will experience a negative shift and a positive shift as the amplitude decreases. And here we actually understand that the negative phase shift is representing a negative force gradient, which is attractive force, and a positive phase shift represents a positive force gradient, which is a repulsive force. This attractive repulsive force also will be impacted by how much power you put into that. Here, these are a bunch of phase curve which represent attractive and repulsive force here in the graphics below. As we drive the tip to oscillate at smaller amplitude, in this case in this red line below 5 nanometers, when you use a different set point, you can see there's a big range, percentage of range here are negative. In other words, that tells us that if we drive the cantilever to oscillate at a smaller amplitude in a very wide range of set point, your force is going to be attractive. And if you drive the tip to oscillate at higher amplitude, in this case in higher, this blue dark curve, now, and then in a very wide range, it actually tip and sample in a strong repulsive force. That's interesting. That's because that basically tells us you can actually control the attractive repulsive force controlled by driving the tip at a different kind of power or different amplitude. The actual world situation is actually more complicated, and to discuss about it requires more time, so we'll not get into more detail into it. Now here, this is a simplification of the points I just discussed, that if you drive the tip at a very small amplitude, when it oscillates at only 10 nanometers, in a wide range of set point, the force will be negative or attractive. And if you drive the tip to oscillate at large amplitude, in this case 150 nanometers, in a very large range of this set point, the force will be positive. That's great. Let's take a look at the attractive to repulsive region. This is an experiment we did that, and this color here in this image represents phase. And this image is the driving is very low. As we increase the drive, you can see the phase start to shift from negative to positive. What does it tell us is that by increase the drive a little bit, the tip and sample interaction is shifting from attractive to repulsive. As we keep increase the drive, the phase is getting more and more points, spots where the phase shift to positive. That it tells us that when you using this parameter drive, you can manipulate attractive force and repulsive force in a very controllable way. Actually, this is a more positive and more higher drive, and then you can see the repulsive regions getting higher and higher. You're gradually shifting from attractive region engage to repulsive region engage. Now, this is very interesting because it actually can allow us to use this phase image to study the mechanical property of the sample by looking at the phase image. Here, it's quite complicated, but in order to understand it, we're going to simplify the story to this point that if we use a very high drive to drive the tip to engage sample to do high force tapping, when we do that, a more stiff sample region will give you a more steep spring constant, and therefore will cause the phase image to shift more positive. In other words, if you do a hard tapping, the phase image actually can kind of resembles the stiffness mapping of the sample. And here is an image of a polymer blend in this white area. Here the color represents phase. This white area is made of harder polymer, and these dark area represent softer rubberish kind of particles here. So this gives us a means to differentiate materials in its hardness by tap the surface at a higher drive. When you tap the surface at lower drive, you can actually measure the energy damping, because you know that when we drive the tip at a smaller amplitude by lower drive, the tip and sample is in attractive region, and therefore the phase is no longer represents the stiffness, it actually represents the energy damping. And then in this case, you can see that these surfactants shows as higher phase shift, and then which tell us these are higher energy damping of the surface. So by manipulating the engaged tip and sample at attractive or repulsive region, you can differentiate mechanical property using phase image. Okay, so how do we use this knowledge to help us to improve the resolution of image? How do we do this? Here is an image of imaging of a tapping mode on a grade, and you can see that this edge at the beginning is kind of sharp, and then gradually it turns into some kind of blunt. That is because when we use high drive to image a sample, when we do high drive, from the previous discussion, we understand that tip and sample is in strong repulsive region. The tip is hammering into the sample, cause the tip to lose its sharpness. And this losing of sharpness is actually the major reason why we do not achieve high resolution. You might think that the instrument resolution is defined by hardware and computer bits and so on and so forth. Actually, the limiting factor is not. The limiting factor normally is how sharp is the tip, and you need to understand how to protect the sharpness of the tip in order to achieve the high resolution. You could do this by engage the sample in a very small force, attractive force, and gradually shift it to repulsive force in order to maintain the sharpness of the tip. That's the reason that we will emphasize this very important points of how to use parameter to obtain highest resolution. The first, you have to protect your tip. The entire imaging process, you have to maintain the tip and sample engaged, does not cause the tip to blunt. And in order to protect the tip, the most important parameter here is actually drive. If you read a lot of AFM manuals, you will notice that there's not a lot of AFM manuals or books discussed about how important it is to define the correct drive. In my opinion, the parameter drive is super important. That's because this is how you define how sharp is going to be the tip after you first scan. If the tip is not sharp anymore, no matter how good is your parameter, your image is going to be blunt. It will be smooth and there's no resolution, no details. Okay, so let's move forward here. So here's a procedure normally I will ask people to do in order to achieve high resolution. Here's my opinion. That what do you think we can achieve high resolution? Is it true non-contact mode or attractive mode is give you high resolution, or is it tapping mode give you high resolution? My opinion is that somewhere in between give you the highest resolution. What you need to know is how to approach from an attractive or true non-contact mode gradually into a tapping mode until your resolution is good enough. And if you further increase your engaged force to a hard tapping, your resolution is going to start to decrease. So at that moment, you achieve the highest resolution. Okay, here's a procedure. You always start with a smaller drive and then put your set point from high to low in order to get the best resolution. And then you find the best gain to achieve the stable engage, and then you increase your drive incrementally, increase a little bit. And then you optimize your set point, optimize your gain, and then increase drive again. As you can see, you're gradually approaching from attractive region gradually into the repulsive region. You start with a true non-contact mode, gradually shifting yourself to light tapping, a little bit high tapping, in order to achieve the best resolution. This will give you the manipulated parameter so much easier approach by just changing one direction of one parameter, which here I will keep emphasize myself, the drive. And here's how do I achieve the high resolution on this protein sample. This protein sample, as you can see here, you can resolve the sub-molecular structure of this protein. And I did this by using a very small drive and gradually increase until some details start to show up. Here's another GIF file and show you a polymer sample. And this is a series of images obtained on the exact same sample. Nothing else changed. The only parameter I changed is the drive. By lower the drive, you can see the very surface, the top head groups of this polymer. And then as you increase the drive, the lamella structures start to show up. You can argue when you engage the sample in a true non-contact mode and you see tiny little grains, is the high resolution. You could also argue you see the lamella structure and those beautiful lines, those are high resolution. I'm going to have to say all of them are high resolution. You're just experiencing different layers of this high resolution. And this image series clearly demonstrated that the importance of drive enable you to achieve the best resolution in any kind of situation. And here's the conclusion. And thank you for your time. Have a nice day.